Hi everyone. So let's prove the extension of the previous problem. So it tells you if R is a rational number and A is an integer such that you raise it to the power of n and you get A, proves that R is an integer. So let's prove that. So what is interesting is following is that first assume that R is a rational number. So that means we can write R as Z over W. We'll prove that W is equal to 1. So first, by assumption, we have the following. We have that R to the n is A. So that means that Z to the n is equal to W to the n times A. So here, by the prime factorization theorem, we have the following presentation for Z, W, and A. So Z is equal to P1 R1 up to PK RK. Same thing for W. W is P1 U1 up to PK UK, and A is P1 L1 up to PK LK. So we have the following. So we have Zn is Wn times A. So from that, we have that P1 N R1 PK N RK is equal to P1 N U1 up to PK N UK multiplied by P1 L1 up to PK LK. So assume that that Z and W share no common factors. So there exists a PI such that PI doesn't divide W, doesn't divide Z, doesn't divide Z. Therefore, that means that PI to so that means that so Z is W is all of those i's. So then that means that Ri, therefore Ri is equal to 0. So we have the following. By the uniqueness of prime factorization theorem, we have that n Ri is equal to n ui plus li. So if Ri is equal to 0, so that means that n ui plus li is 0. So in particular, li is less than 0, contradicting the fact that a is an integer. And we're done. So the assumption that we started out with, that we have primes dividing like that, we can write W as bunch of prime factors came to the conclusion that we have that a is not an integer, and the contradiction came from the fact that pi doesn't divide z. So here all of the factors of w divide z, then it cannot be any prime. So that means that w is equal to 1. So therefore, w is equal to 1. And we're done. Yeah, I hope you guys enjoyed the video, and I'll see you in the next one. Bye.